Hello everybody. One of the fun things you can do with torque is you can sum all of the torques on a system around a common axis to be zero. And this just means no rotation. Because as we've seen, even with the work and the kinetic energy, that if you apply a torque to a system, and if that system is able, it will rotate. We'll couple this with summing of the forces equal to zero, and that means there's no acceleration. And both of these conditions are applied when we're dealing with something called equilibrium. Or, as the engineers like to put it, statics. The case when absolutely nothing is moving. So let's give a couple of examples of what statics look like, and we'll see if you find them useful. Okay, so let's take a heavy pulley, and by heavy I mean it's going to have a mass and it's going to have a radius to it. Let's make the mass something comfortable. How about 0.4 kilograms? Make it a big enough radius. 0.0, let's say, don't want to go 2, let's go 5 meters. And what we want to do is take a rope and go around the pulley, yes, and then we will hang two masses off of the pulley. So mass 1 over here, let's say it's 1.3 kilograms, and that that's what we need to know. And that the mass over here is 1.5 kilograms. Normally, without the pulley having a mass, we would just assume that the tension was constant throughout this system, the whole system. But instead what we need to do is to break this system up into 3 systems to get analyzed. Let me just do one more thing. I'm going to come in here and I'm going to provide an anchor for the pulley off a ceiling so that it's a complete system. And I'll show you what I meant by a complete system. We'll do our usual trick. Of not having a question. But that's going to be one system. And then we'll take the pulley to be the next system. And then we'll take this last object to be the third system. So that's 1, that's 2, and we'll come over here and call this 3. To turn this into a good question, I want the mass of this object of system 3 to be, it's not a question mark, to be our unknown. So what I've basically done is the parsing step. So let's divide it. Into our approaches. Okay. Let's dive back into blue. And let's start with the easy one. Let's sum the forces in the x direction. Let's sum the forces in the y direction. The sum of the forces in the x direction, that would be our horizontal direction. So usual xy coordinate. There are no forces in that direction, which is good because we want that to sum to 0. The sum of the forces in the y direction are going to be given by it's going to be given by 4 different forces. I've got the force of the hanger. I'm going to have a negative weight, and I'm going to have a negative tension going to system 2 and a negative tension going to system 3. And that all has to equal 0. So what we learned from summing forces in the y direction is that the force that is holding the pulley up, this one, has to hold up all the weight. The mass of the pulley and the mass, and the tensions associated with the relevant masses. We're still dealing with system 1, so we have to do the sum of the torques about the same axis in system 1. So I want to make that clear. We're doing system 1. And the sum of the torques now, what I like to recommend you do is to take every force that's acting in system 1. So pulley, tension from 3, tension from 2, the force from the hanger, and of course everyone's favorite force of gravity. Which I suppose is what I should have called that. Okay. So when calculating torques, it's useful to list every force we've got. So I'm going to do, oops, it's not where I wanted that. And just a listing of forces. I've got FH, I've got FG, I've got T2, I've got T3. Let's go in and make sure it's clear that this is our rotation axis, the red dot. And let's apply the torque to each of these cases. So the torque is going to say, I'm going to have my full radius. I'm going to have a radius from the axis crossed into where FH acts. I'm going to have the radius, the distance from the axis crossed into FG. I'm going to have the distance from the axis, crossed into tier 2, and the distance from the axis crossed into tier tension 3. Okay. So notice that RA is the distance from axis to where the force is applied. And the reason I wrote that in red is if we now take a look at RA cross FH, where the pulley is hung about its axis, the distance from the center of the pulley, which is our axis, to where the force responsible for providing that access is acting, that distance is 0. Likewise, for gravity, we always put the gravity at the center of mass of our system, and since the center of mass of our system is where the axis is rotating, the distance between the axis and the center of mass is 0, so the distance between the axis and the center of gravity is 0, and again we can eliminate one of our torques right off the bat. The other two, going out to R, the radius to torque 2 and the radius to torque 3, is findable just by doing our vector trick. So let me expand that RA for number 2, tension, is given by the radius of the pulley and nothing happening in the Y. And that's going to cross into tension 2, which is no action in the X, but action downward in the y, so I'm going to have negative T2, tension 2. So, what we need to do is multiply this out such that we have and can use FOIL. So let me write it as R I hat crossed into minus T2 y hat. Same vector, just written in a different notation. We go to our circle to figure out the cross product. So I get R, wait a minute, I can't have them both. I'm going to have R T2, tension 2, and then I'm going to pull the minus sign out because that's also a constant, and we're left with x hat. Oops, I was right. I'm sorry. X hat here. That's the cross product. All right. So x hat crossed into y hat. And if we follow our pattern, I start at x, I move to y, and then the result is z. And I did it in this direction. So, let me get a pen. I know that negative R1 T2, and that's just going to be z hat on the inside. Okay, and all the way from the beginning, because this will just be confusing, because I worked out the cross product, what we've actually been solving for is the torque due to force 2. Okay. So in a similar logic, let's do the torque around object 3. And that's just going to be R cross T3. And the R is the full radius of the circle, but now we are going backwards. So we're going this way to get R. So I wind up with a negative R acting in the x direction, crossed into the T3 pointing down. You know, just really tempting not to make that a pi. Hey, where'd you go, eraser? Okay. And we'll convert this into something that's a little easier to understand for some. And we're going to do negative r I hat gets crossed into negative T3 J hat. Pull out all of the constants. So negative R, negative T3, and we're going to wind up with I hat cross J hat again. So we can use this same information up here because we're just doing I cross J, and we're going to wind up with highlighting. We're going to wind up with a value that is positive radius T3 as our final answer for the torque in the, I'm writing down Z because it's a habit, but we chose to do IJK in this example, so that's going to be K hat. Sum the torques, and I get negative R T2 plus R T3 and that has to equal 0 because we're in statics. And because we're in statics, I can pull the R out and get T3 has to equal, minus, pull the R out, minus T2. All that has to equal 0. R cannot be equal to 0. So we wind up with the tension in 3 has to equal the tension in 2. For completeness, what we should do is hit up another approach and draw the free body diagrams of the masses so tension, whatever force of gravity, and we're going to find that the acceleration has to be 0 because that's what happens when you sum the forces in statics. So quickly we can find that T2 is just equal to the force of gravity on 2. And by an immediate extension, the tension in 3 has to equal the force of gravity acting on 3. So let's gather up our equations. We know this is true, and we found both of these equations. So in our execute, I'm sorry, that's called evaluation. Used to be called execute a long time ago, but now it's our evaluation. And we write our 3 equations. Somehow I missed that. There we go. That we know T3 is equal to T2, that T2 is just equal to M2G, and that T3 is just equal to M3G. And so let's just plug numbers in. We said the hanging mass of 2 was 1.5 kilograms, which means that T3 equaling T2 is M3G equaling M2G. We don't need the force of gravity, it counters on both sides. So mass of 3, which is what we are looking for, had to be the 1.3 kilograms. 1.3? 1.5. Of the other. Now, this quick solution may seem kind of obvious, but once we leave statics behind and start working with dynamics where there are possible accelerations, going through all of these steps will help you from making mistakes. And we'll start doing dynamics next week. So that will leave this worked example finished.